Go to the Zoom or tap. Or tap. Yeah.
Okay, so welcome everyone. It's a pleasure to have Aiswarya C among us as the colloquial speaker. So Aiswarya is a faculty member at Chennai Mathematical Institute, and she has also a visiting faculty position at IIT Bombay, and she has also been an invited professor at ENS Paris-Saclay, and her research interests include automata theory, logic, concurrency, verification of infinite state systems, and so on. And today she's going to talk about subword ordering and transductions. So over to you, Aiswarya.
Thank you, Shivashish. Thank you for the invitation. And it's a great honor to be here to talk about this. This is scholarship. So I'll be talking about a cybersecurity program of this object. I'll tell you what these are. So they are basically string constraints. So what are string constraints? So this is similar to any of the SAT instance that you would get with variables and constraints. But the variables are going to take string values. And what are the constraints that you can write? You can say, for example, so here the x, y, z, etc. are variables. And you can say something like x belongs to this particular language. You can say that y belongs to this particular context free language. Or you can say that x is actually equal to the kind of definition of y and the z. Or this is some transducer. You can say that x is actually the transducer output of y. Okay, when you give y as input, it will be out. Or you can say the length of x is 3 times the length of y. You can say that x is this special thing. This is what I'm going to call.
So what is a transducer? If you can say it.
I will give you with that. So transducer is basically a string to string function. Yeah.
This is a prefix.
No, this is not a prefix. This is a subword relation, which is a scattered subword, like your subsequence. Exactly. So this is a subsequence of concatenation of y with itself. It's the subsequence of that. Or you can say that next is so here when I say write this as an equality, you think of this t as a function from words to words. Here you think of this t as a relation from words to words, and you say that y should be related to x should be related to y under this particular relation. This is some more complicated thing, shuffle. You might have seen this thing in your automata theory course, like shuffle of two languages, it's like that. So you take whatever word you have in x and z, and you take two copies of the word in x, y, and you shuffle them. And so there are several different possibilities of shuffling them, and it should belong there. So you can write all possible such constraints relating different variables. Of course, these first ones, they are not relating to different variables, they are just imposing domain restrictions on variables, whereas the below ones are kind of connecting different variables with each other. So it's kind of giving some kind of relations between constraints between these variables. And
What is
so x and q, would it cover one of the rest? I mean,
yeah. So I'm just giving an example of what can string constraints be.
Okay.
Yeah. So what was your question?
I mean, this x and q, the last one, is that more general than the rest of them, or that? I mean, is that kind of disjoint from the others?
So it will depend on what you will put in the T. Okay. Yeah. So we will see examples of this.
what is the family of constraints that are allowed here?
So in general, when you're writing constraints, you can allow any of those, and then we will see how the desirability changes. Like when you add some and you do not allow some. That's what we are doing.
Okay, currently you don't have a specific.
No, right now these are like in general when we so in the literature, all of these kind of constraints are being studied. This kind of conditions can be put on variables, string variables. And of course, obviously, we are interested in the satisfiability problem. Given a set of such constraints, the question is, can you find words, can you assign words to each of these variables such that all these constraints are satisfied? Okay. Yeah, this is exactly what I said. Now, going back to what is not. So if you only have equations, you can just write things like x is equal to y z. And then this is parallel.
One more question. This is just it's just a problem of finding strings that satisfy the constraint. It's not optimizing anything. There's no.
No, we are not optimizing. We just try to see if it is actually satisfiable or not. Yeah.
Got it.
Satisfiability is what it is. We are not looking at optimization problem.
Got it.
Okay, so If you just have the equations, this is desirable, it's a similar result by Lacan from 1977. And if you throw in regular membership constraint, this will be desirable. So you can throw in constraints of this form.
But isn't this just the intersection of languages already?
No, it's a bit more complicated because
Because
you can write complicated equations, like you can write complicated expressions on both sides. You can write like x equals or xy equals yx, then also already kind of things that says that they have to be cyclic permutations of each other and all those kind of things. So you can express more complicated things. It's not just intersection of this. And of course, you can also impose more domain restrictions based on that. And of course, if I just have one variable and I put a several of those domain restriction, that's going to be the intersection monotonous problem for those set. But these relational constraints are what are going to cause the difficulty.
Got it.
So this is desirable. If we add, on the other hand, some kind of transductions, which I will say again, more to go with what it is, it's going to be functions from words to words which are kind of realized by this automata. Okay. And then it becomes undesirable. And do not put the transductions, but instead, if you try to put cornerstone membership constraints, then again it becomes undesirable. And if you try to go beyond this regular to something like cornerstone, then again it's going to make it undesirable. And if you just have these kind of equations and you have length, we don't know the status, whether it is desirable or not. It's open. And what we will see in this talk, in this setting, we will not have equations. Okay, we will not see.
So if you
anything.
just have length, then also it is not known, but it or if it like length along with certain things and
Along with the equality. So you put equality, you put equations, and on top of it, you say that there should be some variable. So in the setting that we are going to see today, we will not have equations, so you will not see equality in here. So we will remove the ones that are equality of this, and everything else will remain.
so it is less than equal to the prefix or
No, this is the standard subword, subsequence relation, subsequence relation. There is a subsequence relation, there will be transductions and there will be shuffle. So we will see examples of these things also. And then we will have membership constraints coming from regular and also from context.
But can't I just write x is a subsequence of y and y is a subsequence?
Yes, yes. And
That's
that will
a
make it
equality.
exact. Yes, we can recover current this. I agree. Okay, and in general, the kind of things that you can write, you can use all of these operators. You can set the shuffle of the transducer output with respect to one particular transducer. This one is the same variable given to a transducer again. And if you think of these transducer relations and not just functions, there will be each of these things may be realizing two different output points, potential related values. And you can take yet another transducer if you want under different variable and all that. So you can shuffle all of them, and then you can say that, oh, the value that you want to get in X is actually a subsequence of this big shuffle. You can set these values.
so can you say once more like what are the three arguments? First one, second one, third one example.
So we have we have two string variables here, y and z. Okay, and y is going to be fed into this transducer T1.
Mhm.
It can give you several different outputs because it may not be deterministic. So you pick just one output here, you pick another output there.
Okay.
It could also be the same, in which case it's going to be the same output which is going to punctualize. Okay, and
Then
this
shuffle.
T2 is yet another transducer, so maybe it realizes a different relation. And to that, the input is a null cell. That is going to give you another output. So there are three different words that are going to come, which are in relation to some of the input parameters. And then you take a shuffle of those.
Oh, shuffle.
The shuffle actually, essentially, shuffle is not a unique thing. I mean, there are multiple ways of shuffling it. So you'll get a set of words. You have to pick some word in the shuffle such that X is going to be a subsequence of that.
When T1y is a relation and you write it like this, can I take two different values in the two arguments?
Yeah.
Yes. Yes.
And why do you write like X is a subsequence of Y? I mean, it's like Y
No,
followed
so
by
here
a
I
Y.
meant it's a concatenation. And I write y is a concatenation.
But can can we just have X is a subsequence of Y? I mean, instead of Y.
Yes, that was responsible. So it's giving general some example.
I see. Okay. So that YY is
Yeah,
same as
no.
YZ. Like,
Yeah,
it's
it
just
can be
the
Y, and it can be just Y, it can be Y, Z, Y.
Shuffle operation is just permuting T1 by T1 by T2.
Shuffle is more like shuffling cards. It's not permutation, so you take the words, letters, and you kind of interleave the word. And the relative order is kind of maintained in each of the word. Yeah, so for example, the concatenating Y, the first thing, second thing, and third thing, that is one possible way of shuffling them. Permuting them is another way of shuffling them. Interleaving the letters is yet another way of, there are many things. The order with respect to one particular word is preserved. If we just project it to the positions that are coming from one word, then they have to be linearly ordered according to that. So easy, I'll show you some examples. So we will not have equations, but we can generally write equations of this form. So basically we do allow contextual membership constraints, subword relation, shuffle, and transduction. So, and of course, I will explain what these objects are. So first of all, what's the subword relation? We can just drop some letters and get this one, the subsequence. So this ABA is a subsequence of this one. For example, you can take this A, then this B, and then this last A, for example. It just needs to appear in the order. This is given. So and shuffle, as I was saying, is exactly this. So for example, if you take this ABA and shuffle it to this BAA, of course the concatenation is the first one. You can also concatenate the other way around. You can also put this thing as an infix, but it need not be a contiguous infix also. It can be scattered, like like this one, and there are many other ways. This is the shuffle, and that is going to give you a set of words. So just to give you an example, suppose my constraint is this. There are these three constraints. Okay, I have two variables x and y. I want to satisfy that x is a subword of shuffle of y with y. X should come from this regular language, so it should have, I mean, it's a non-negative iteration, right? So no, I mean non-zero iteration. So it means it should have B and followed with three A's, the smallest word that can be there for x. And y can be either an A star or a B star. This thing, is it satisfiable?
Yeah. Yes.
It is not satisfiable. What value will you give to y?
Oh, they're the same fire. Okay.
Yeah, it's the same y. So you have to give one value to y and one value to x. Give a value to x, you find a value for x and find a value for y. Can you find a word for x and a word for y such that this is satisfied? All the three concepts. It is not satisfied because, of course, you need in y both. I mean, inside the shuffle, you would need both A's and B's, but whatever thing you pick is going to be either only a sequence of A's or only a sequence of B's. So x needs both B and A. So you cannot satisfy this one. Right. On the other hand, if I instead of this y, I use y and both of these things, I put both of these variables, I put the same constant. Then for y, I can put some A, for z, I can put some B's, and then I can shuffle them and I can get my required BAA, and that's fine. So this one is satisfied. So it's the problem place. We have not seen what transducers are, but at least the setting of how the constraints are given and the question that we are asking. Okay. Now, just to tell you, so you were asking about that y. So that's a concatenation. I do not have explicitly that thing here. Just to tell you that shuffle is actually a powerful operator to make sure that we get concatenation also on top of it. How do we get that? So for example, if I wanted to say that in a x1 this is a word of y, x2, x3, this is the proper concatenation. I don't explicitly allow that in my syntax. But in order to get that, what I can do is I just use some 3 extra auxiliary variables. So x1, x2, and x3 had some membership constraints, some languages associated with it. What I will do is I will use these 3 new things, and then I will put this x4 is this x2 followed by dollar. That is what I want. So I will just put a dollar, a special symbol at the end of all the words in L2. in X5, I'll put a dollar before every word in L3, and in X6, I will put this double dollars between L2 and L3. So somehow this X6 is supposed to mean the concatenation with $2 in number. That's what I want. And then what I will say is, this X4 is actually a subword of shuffle of the X2 that I get from here with a dollar. And X5 is going to be a shuffle of X3 with a dollar. So there are now all possible ways of shuffling these two things. So you can take a word from X2 and put and insert the dollar wherever you like. But because of this particular membership constraint, if I put that dollar somewhere, I mean, that dollar should somehow go in the end only because X4 has to solve the shuffle will, there's only one particular way of shuffling which is going to satisfy this, and then X4 is going to be from this L2 dollar, so that particular word itself can be that without losing anything. You can also do something, but that is still okay.
But you're already using concatenation. When you say X4 is an L2 isn't that concatenation?
No, so this is just a membership constraint. The automata level, I can do whatever.
Yeah, but you're concatenating dollars to the language.
But that is okay, right? I mean, I give a new language for that. I just give an automation for that. Automation or Montessori language or whatever. So since Montessori languages and lines of loss and concatenation, I can just get a constraint for that.
Okay.
So my problem is I cannot say that in X2, it's actually exactly X2 concatenated with X3. This is my problem.
You can't have two variables concatenated.
I cannot have two variables concatenated. The language level L1.L2, L1 plus L2, L1 star, or this.
These are not.
These are okay. These are okay.
L1 star is allowed.
Yeah, because that's that another language. I just changed the.
Okay.
It's a reduction. I changed that. Then after doing all these things, if I just say that X6 is the thing that you're going to get from here, it's a subword of the shuffle of this X4 and X5. Okay, so X6, what you're going to get here is some word from L2, then $2 and some word from L3. If that is going to be a shuffle of this X4 and X5, those $2 which are present here, they have to go next to each other. I mean, it may be possible that this dollar goes to the second one and that this dollar comes as the first one, but doesn't matter anyway, the dollars are going to be next to each other. So whatever word that you had in as the word part of this X4, that has to come before the dollar, and because the order is preserved, and whatever word that came as part of the X5, which came from this L3, that has to be after the dollar, because the relative order has to be preserved. So the shuffle of X4 and X5 will somehow, I mean, you have to have the word part of this X4 as in the first and the word part of X5 in the second. Okay, and then X6 is going to be subword of that. That's kind of more or less saying that this X1 is a subword of X2 with this exponents. So this part with this part, we are kind of requiring that that concatenation. So shuffle is more powerful than concatenation. So we don't explicitly we will not be putting concatenation, but concatenation can be recovered using shuffle. So coming back here. So we have subword relations and the shuffle operator. And transducers. These are relational transducers. What they will look like financial automata. So of course, this first thing that you read is the input, and every time you take a transition, you will also produce an output. Okay, and then when you finish reading a word, you should be in an accepting state. If you started initially, you have finished in an accepting state. You concatenate all the outputs that you have produced along the path of this accepting run. That will be the output corresponding to that one. There will be multiple outputs. So we will see an example here. So for example, on the word ABA. So you can see that this right hand side of this transducer, what it does is it will just leave every B as such, it will double every A. And on this side, what it does is it will duplicate every B, but it will leave A's as such. So if you read ABA, it may have one run on this side, which is going to give you double A, then single B, then double A, just on this side. And if you look at the run on the other side, it's going to give you A, B, B, and A. Okay, on every word. So this particular transducer will have two images, two outputs. but we can have general output arbitrary. And if it for a single letter A itself, you can have just A itself as the output or two A's as a. It's also depending on which side you do this. Yeah, so these are NFAs, your epsilons are allowed. Yeah, and they will have all this. So now let's look at an example again. So I want my X to be BA at least, and several conditions of that. And Y can be either an ABA or A star or B star. And I want X to be a subword of shuffle of. This is the transducer that I have and of this Y. So can you give values to Y such that all these constraints are satisfied? Since I want both B and A here in the X, I have to pick this word which gives both A and B, AB and A. And then to match the count, so this has at least 3 A's, this has also at least 3 A's.
No, but if you pick that word, you will always have A at the beginning.
Even you have B star also.
No, it's TY, so if you put Y equals to ABA,
But you don't have to put Y equal to A.
but then you'll never get
You
A.
can take either B or A. Y equals B also.
But then you'll never get A, so then it's not have A.
X needs to have A and B.
So Y has to be ABA.
It's the same Y on X.
But then
It's the same Y for both couplings.
Yeah, no, it's the same Y that you give us the argument, so there are
And then
two
the-
variables, so I will find the value for X and find the value for Y.
But the
transductions can be
transductions
different. Exactly, the transductions can be different. Because there are like multiple outputs, each time I invoke this transducer, it may be going to give me a different output, so that is allowed.
So let's.
So if you choose Y equals A B, then we have to have an A. That won't work.
What, why wouldn't it work? I don't understand.
If
So
Y
ABA,
excuse me, if Y is ABA,
Yes,
then after you shuffle, you have to begin with an A. Because no matter what. you
yeah, but
do-
I can lose things, this is a subsequent.
Oh, there is a
subsequence, yeah.
Oh.
No, you
Oh,
can drop
that you now will drop.
Oh.
Yeah. So you only have to cover this one, you have to get a long enough word there which will cover this. Yeah, so you need to just get something so that when you shuffle them, you should get 3 B's and 3 A's. Okay, so for example, if I want to take one ABA and I pick this thing, it will give me 2 B's. And as one other output, I'll pick this one when I get 1 B, so total I get 3 B's.
But you also need alternation, right? Those two B's cannot be
No,
together.
shuffle can do all the alternations.
Oh, okay.
You can take from both sides.
Okay, got it.
So.
Yeah.
Yeah. Awesome. There are multiple ways that I'm saying that this realize. This is one possibility, this is another one. So this is an example where I picked. One was ABBA and the other one was AABAA. And I shuffled like this. In this one, I picked ABBA on both of the transducer. That also worked. So there were 2 ways that this was satisfied. It's satisfied. On the other hand, if I did not have this ABA, if I only had AB there, then it is not sat. So yes, the letter count will not do it because 3 A's and 3 B's I may be able to get, but the ordering is important now. After the first B, I should have 3 A's, which I will not be able to get.
Okay.
So in general, we can write equations of this form, like not equations, constraints of this form, that it is a word of shuffle. Then you can write T1 of Y, T2 of Y, then the T2 of the same Y again, but this may be taking a different value. Then T1 with a different input Z and all. So variables on which, so this particular constant, if you look at it, it has three variables, x, y, and z. Can you find values to x, y, and z such that this constant exists? This is the question that we are asking. So this is our theory. So we are given a set of bunch of such constraints. The question is it satisfied? And as expected, it's undesirable. So already if you have this constraint membership, as you just noticed, we can just write x less than x is subword of y and y is subword of x. You are kind of recovering equality back. And then you have constraint membership constraint. This is essentially, if you have this constraint, this is essentially asking whether there is a non-empty intersection for L1 and L2. Right? If you have a non-empty intersection, of course, you can put the same word for x and y, and that will satisfy this one. And the solution would indicate that the intersection is non-empty, which is an undesirable for intersection.
So your L1 and L2 can be context free.
Yeah, so here it is context free membership, which is undesirable. No, yeah, so this is the classical program that we will see in the theory of competition. Of course, we can do it from by reduction subsets. Intersection of class of points for lengths. Okay, so this is undesirable. On the other hand, if I only allow, so notice that here I did not use shuffle. I did not use transductions. I only had the subword ordering and the constant membership, which was the very limited setting and instance. Now, if I do not want to allow context free, I have regular membership. I also throw in shuffle. This is again the regular side. And this is a reduction from CCP, which I will just go through. So suppose we have this two functions f and g from A to B star, and we want to see whether there is a sequence of indices, I call it I, such that f of I is g of I. This is the PCQ instance. You can think of f as the words in the top row of the domino, g being the bottom row. The reduction will just use four variables. I will use the same variable I to, because if it is satisfiable, I want that I to be this particular sequence, which is going to make this f of I and g of I. Okay, and this S is going to be the value of that thing, f of I or g of I, the solution. And then this f and g are some extra variables which is supposed to indicate these functions. So of course, I want this I to be a sequence of these indices, S to be the solution, so it should be coming from B star. And this f and g, f will be like A followed by the f of A. Okay, and it will be always like that. Any word in which you have an index letter and then followed by the word in that. And here the same thing with G. And then what will be my equations? I will say that now this I should be a subword of this F, it should also be a, so this S should also be a subword of F. And this F should be a subword of the shuffle of I and S. When I put these three things together, so notice that, assume that for example A and B are disjoint alphabet. Then you will see that if I put these three things together, then in this particular subword here, I'm not losing any letter. Because I already want the I that I put here to be a subword of it. And here I'm saying that F is a subword of I, shuffle of I with something. This S is going to only give me letters from B. So the A letters have to be preserved. I cannot lose any of the A letters. Same way, I cannot lose any of the B letters coming from here. So this, even though I put this subword here, like subsequence here, so almost saying that F should belong to the shuffle of I and S. I cannot lose anything. I cannot lose any letter. So I have the letter sequence.
I'm confused. So F, is it a function? Is it a string? What is it?
So here F is a function. Here I'm using it as a string to denote that function. So I'm going to put the input value to that F followed by the F of A. That's what I'm.
What does it mean for F to be an A, F of A? In this time, that time.
I should have used different letters. I use the same letter so that I make parallels with this one. So here, maybe I should have used a different letter here. So this F here, this is actually a string variable.
Okay.
This F here, it comes from the PCB input instance.
Okay. I see. So F is that with star and G is also the same idea. Okay. And I is subword.
So for example, if 1 is getting mapped to AAB and 0 is getting mapped to BBA, this will be like 1 AAB, 1 AAB, 0 BBA, all those sequences that you can get like that. So it will be a sequence of distance for
Okay.
Then suppose there is a solution, suppose there is an index, then I am saying that this F thing that you would get in that should exactly be the shuffle of that.
Cannot drop anything because
Yeah. And I said that this index sequence should exactly correspond to the index sequence that you get from it, and the solution sequence should be exactly the projection that you get from it. And I will write the same things for G as well. See, these are the 6 relational constants I will write. This is my reduction. I will use just these 4 variables and I will write these constants.
Sure.
So if it has a solution, then it essentially means that the VCQ has a solution. If it is accessible, then it means that the VCQ.
Let's see here.
Same index and sequence and the solution can be shuffled in different ways. One to match the F function and one to match the G function. If you want to think of it like that. The way you try to align it along with F is the word that you get here, and when you are aligning it with G, that is the word that you get here. And both words, when you project it to just the A letters, you should get the I. When you project it to the B letters, you should get the S. Okay, so this is understandable. Even when you do not have honest membership, but you have shuffle and regular language. And these are very simple regular languages. Not complicated.
Sorry, so the I is the indices of the dominoes in the.
Yeah.
Okay.
Yes.
Okay.
Yeah. I is the intercept of the dominoes, and F is the top word, G is the bottom word. Written on each of the time.
So if I gives a string and GI also gives a string, and then we're asking if the match. I mean, I belongs to a class, so.
I belong to I is the sequence of
Sequence
indexes.
of this thing,
F
and
is the solution word, which is going to be the same word which you're going to see on the top and on the bottom. And now I'm going to arrange the words like first the index name or the tile name followed by the top, again the tile name followed by the top, etc. If I write it like that, then I should get the word from F. That kind of says that the top is kind of matched. And here you are rearranging it in a different way. The tile name, the bottom word, tile name, bottom word, etc. And then you will get the G. So because of these two things, you are not losing anything, so it has to be exact shuffles. And if it has a solution, it means that if it's accessible, it means that it's okay. If you have transducers, I now have removed the shuffle, but I have put the transducer instead. That will also make it understandable. The same production in a slightly different way. The same PCB problem. And these parts also remain exactly the same. 4 variables and the what it's supposed to do. Now I don't have the shuffle, but I have to get back that thing somehow or other. So I will use 2 transducers. This one transducer, what it does is it will take a word. So the word is the input. The input word here is going to be a sequence of these indices, okay, or whatever, some word. It's going to throw in a lot of B's in between every letters. So it will see all of this input word here on the output, but between any 2 letters, you can see as many B letters. And here, this transducer A, it is going to throw in as many A letters as you want in between any 2 letters. And then I will write the same thing, like I will say that, I will say that this particular F is going to be a subword of this index sequence in which you throw in the B.
Hmm.
You will also say that it's actually a subword of the solution sequence in which you throw something.
How do you even do this with a finite transfer? How do you write the B star?
Oh, that is it. I mean, because I have
Just
epsilon.
finding even.
Oh, you can have epsilon?
I have epsilon.
Okay,
I have epsilon.
got
Epsilon and time
Okay.
variables.
Got it.
Just at every node we just make it proper. Okay. And the same thing for chat. So the same production in a slightly different one, but then now if instead of shuffle, if you had transducers, again you are in the same situation, it's undecided. So I told you before that shuffle is powerful to capture concatenation, but what if I do not have shuffle, I only have concatenation, I don't. This is all. I don't know whether it's decided.
How long do you have it?
3 years.
Let's wait a couple more years before. It's a bigger topic.
You know, we have thought about it quite a lot, we don't know. So this is the picture, everything is hard, like undecidable, and with this, if you do not have the shuffle, but you only have a concatenation, you do not know.
So what were the results before these things came out? Like, so you had like,
So
you showed certain things in the beginning, right?
yeah, that is with equality.
That is
With equality, the only thing that you can add on top of it is just regular constraints. It still is desirable. The moment you move into context free, the
it
moment
becomes
you,
undesirable. So those things were
transduces, yeah, it is. With equality, with length constraints, it's still open, and that has been open for many years.
So equality and length constraints.
Yes.
And there also you don't have the regular, this something comes from a regular language that is also there, or?
No, I don't think that is also, that's okay.
No, so I'm saying equality and length constraints.
Yes. Like-
Without the regular.
Yeah,
thing
even there
constraints.
is not.
So sometimes adding more constraints may make things, whether will it make it easier, the problem, like if I now additionally add,
Maybe.
add the regular constraint, then
It
it
may-
might become easier. or-
Yeah, might.
I don't know, I mean, I'm just saying like now you're adding some constraints, like you say that, oh, it should come from those regular languages and
No,
maybe
but-
Oh, I see what
that
you're
may
saying.
make it easier, but I don't,
Yeah,
but it
a
may also make it
specific-
more difficult.
A specific instance may be made easier.
Might be made easier, so
I
we
don't-
can immediately
not-
say that the rate is not satisfied or something. But desirability, because of course, if for that bigger thing it is desirable, then you can also not give the regular constraint or keep the regular constraint which it must have. And then desirability it may be a problem. For one particular instance, it might make it easier. Like drawing
Yeah,
more
I'm talking about
constraints.
decide, it's not clear, like
Yeah.
whether adding these extra, like the regularity things, whether will it make the overall problem easier or more difficult?
Yeah, or
It's not
maybe-
clear.
If you just say Excel and empty set. Decidable very fast. But what is the status for integer programs? If you don't have strings, I do not even know that. How would you?
Integer linear programming,
Yeah, let's say. Is it decidable? Is it
yeah,
undecidable?
it's desirable.
It's decidable.
What is it?
Yeah,
It is an NP.
NP.
no, but if the, oh yeah, sure. Of course.
Yeah.
Wait a minute. What if I do something for that style?
No, so there is an abound or solution size length.
No, I don't have that. All the variables are in C.
No, so for the integer linear programs, if it is satisfiable, it will be satisfiable with the solution of some bounded length. So then you can, then you have a bounded size space, so you can only simply guess and check whether it's actually satisfied.
Is there a version where for numbers that is undecidable? If I don't want to work with strings.
Like something that is of all numbers which is undesirable, but not with this.
No, but I'm thinking things like, suppose it's not, suppose it's integer that's not linear, for example. Something.
This is development and equations for the.
That,
Is there-
in fact, these things also have a strong connection with definite equations and from the reverse problem, so that when I said it's open for a long time, it is. Connections were made maybe in the 60s or 70s, but it has been open since then.
Polynomial equations for it. So the polynomial version of it.
Polynomial type and fields are undecidable.
Yes, integer, so you want integer roots of polynomial equalities.
Integer roots of polynomial equalities.
Equal.
Okay, they're undecidable. Okay,
So anyway, we are faced with all this undesirability. Now we will.
and what can you do with length?
What
What did you say about the length?
It's open.
This is concatenation at length. This is the open formula.
No, but what is suppose I write the length of x, what can I do with that? Can I
So I can say that the length of x is like 3 times the length of y or at the most 3 times.
say it's the length of y squared?
I mean, at the moment, no. So that probably is undesirable because of, I don't know, I actually do not know. So already this kind of linear length constraints. This is what is open.
I see, so you're
Yeah.
talking about linear.
Yeah, linear length constraints, not just equality, but you can also put greater than this. Multiply the constant.
Got it.
Okay, so this is the classically studied part with the equations. What we are studying is with subword relation. Once we come to subword relation, okay, these middle two rows are not exactly the same, the titles are not the same, but the constitutive membership, of course, both things are undesirable. Regular and transducer, also it's undesirable. If you have concatenation, here it is desirable with the equation, and here it is open. And concatenation and length, I mean, I don't have a counterpart there, but regular first structure is also desirable. Now, what we look at next
Can you
is.
go back? Concatenation plus. So why don't you have a counterpart here?
I did not write it. If it, that's also open, I don't know.
Oh, okay. So what is
Concatenation plus length with equalities is open. So I said that regular plus concatenation is open. So at the moment, I have not even thought about regular plus concatenation plus length. That's also open at the moment. Yeah.
just concatenation plus length in subword relation that
Yeah.
also is open.
Yeah, we have not, I mean, with the length, we have not spent much time. With concatenation alone, we have spent like a few years. Okay. So to get some desirability, we will now restrict it to acyclic fragments. We do not want equations. Then we can write x less than y and y less than x. We are getting back equality by 3. And that is by making a cyclic relation between x and y. That is what we want to forbid here. And makes it acyclic. Okay, so essentially, whenever we write something like this, you want the between the variables, the dependency between the variables to be acyclic. If you can impose this, then things will come desirable. Okay, so somebody will write the text is a subword of y. So we just put an arrow from the left hand side to the right hand side or the other way. However we want. We want fix one direction, we put it like that. And if the resulting graph is cyclic, then the dependency is cyclic. If it is acyclic, then we will show on this side. So this is what we will have. Okay. So what we will show is that in the acyclic setting, we have desirability and we have some kind of upper and lower, matching upper and lower bounds for both these things. So this non-deterministic exponential can complete for everything except for context free plus transplaces. That will make it one more exponential. I think then it kind of goes through. How much can I do? Maybe I can just see the idea of this one. So how do we get the non-deterministic exponential time upper bound for this one?
Also complete, yeah.
Hmm?
No, it's fine. It's fine.
So since it is acyclic, we will just look at some kind of topological sorting and we will look at the smallest variable, which is not, which is going to be on the left hand side of every equation. So it's going to be this, we can use small letters from it and it is still going to be on this one. So for example, if it is just on a word, if we had a run, we can kind of look at the places, basically pumping down. We can pump down the run on the right side of it and we can get a shorter word. So if you had a long word that satisfied the equation, this was the very small, the first of the words, right? So even if you put a subword that you get by pumping down that big run, that resulting word will also satisfy all the string constraints that you had. So the constraints that you had was that an x was a subword of something all the time. If you replace that x with a subword of itself, it is still going to be a subword. Subword is a non-stimulation. So this kind of pumping down is fine for a regular length. So if the membership consent is regular, this you can pump it down and you can get something there. For contextual language also you can do that same pumping, that is also okay. The problem is when it is not this smallest variable, when it is a next level variable, and it is already also used to cover some other letters from below. You have to pump down. So what you would do is you will just try to identify some places which was actually used to cover those things. You don't want to remove those things essentially.
Sorry, I didn't understand this thing. What do you mean by cover? Next level variable means?
So next level variable, I meant that it is not in this. So we are in acyclic pattern. So we have an ordering between the variables. Take some topological sorting of this variable. So the first we were saying about the smallest in this topological sorting, which is not used to something. So it's always on the left hand side of any of the equation, and that was fine. It was never appearing on the right hand side. We can represent the subword of that. That was okay. Here we are picking a variable which can potentially be used also on the right hand side. So when it is used on the right hand side, the constraint can be something like an x is a subword of y, or x is a subword of y along with something else, shuffle of y with something else. So maybe this letters of y was used to cover some parts of x. So now I cannot completely go on shrink these things because this part might be useful. Okay. Whatever I shrink may actually be used to cover these things and I cannot just remove them. And in fact, so this is actually done for the transducers. That's why there is a block, but maybe let's forget about transducers, but just look at, we are actually, I use this thing also for that. But anyway, so the thing is that, okay, the star ones are the ones which are actually used to cover something from x. So for x, I have gotten a very small word by pumping down.
But you could also get many words, right? You could have many different candidates for x. Why would there be only one? So suppose you know that x is either AB or BA, then you cannot pump down, right? So you have to consider both of them.
So what we're saying is that suppose it has a solution. So x has a value, y has a value, etc. Then we are going to say that if it has a solution, then there will be a solution in which these word lengths are going to be bounded, going to be at most exponential in size. If we can do that, then we can just guess these words and then verify them. This is going to be our non-deterministic exponential algorithm. We are going to guess the solutions which are going to be of exponential size, and then we will just verify that all the constraints are satisfied. Okay, so for this, if it was solvable, if it had a solution, take that solution, whatever it was. I'm going to extract a small solution from that big solution. And in that thing, the first step was look at the smallest variable x, okay, which is only appearing on the left hand side. There I will just pump down. Okay. It can be also membership constraint, can also be a contextual constraint, even if it is the same. In the tree also pumping down. You pump down in contextual diagram also, you will get a smaller word. Size of the smallest word that you will get will be at most exponential. You started from whatever thing that if it is very long, you can kind of pump down parts and then you will get more and more compact words at most exponential. In the case of regular, that this word length is going to be linear. You will get whatever original word you started with, you can, whenever you see the same thing repeated, you can pump down that part.
Linear in what? Linear in what?
In the size of the automata.
Okay.
Because you're going somehow the smallest part, you don't have to go with stakes. Contextual is a bit more complicated, but it's still going to be exponential. In the number of non-terminals of the grammar.
In the number of?
Non-terminals of the grammar. So now we are going to look at this y, and this y is going to be, we cannot just brutally pump down like we did before, because some of the parts from this things that we're going to remove may be used. And those parts is what I'm going to use with these stars. Why do I have these so many different lines? Because each of these lines is going to give some of the transducer output, or I run in the transducer. The same word y, but it is going to be used in all of these different contexts. At one place I wanted to take the T1 of y. Here also I wanted to take a T1 of y, but it might be a different output. So it may be a different run. So think of each of these lines as different runs on the input y in whatever transitions was given. And some of these transitions that were taken in these transitions were important because the output produced in those places were used to cover this excess, this small excess. So that is, those important ones are the ones where I'm going to put the stars. The number of stars is not going to be more than the length of x, which is going to be exponential. Right? So I need to cover all of that x. I look at which all things were used to cover it. That it will not be more than the length of x. So I will put those stars. Now between the stars, whatever length is there, I can put it. That is more or less the idea. So between two such stars, we can consider this length is going to be exponential, etc. And then the number of stars is also going to be exponential. The exponential length exponential is again exponential. That's what you would get. So we will project back into this y and find those stars, and what we will do is something like this. This number of stars is going to be here. If there were like 5 different copies that were running, it will be going to be 5 times the number of x. And then I will look at what were the product of these runs when the same states repeat, and then this should make that lovely. So if it was in the case of regular, then hence we get a non-deterministic exponential time up upon. I will not go through the context thing in detail, but it's the same, more or less the same. You will get a non-deterministic up upon. Here the thing is that when you have think of this thing as the start positions that I want to preserve when I'm pumping down in a context frame thing. So this structure which came to the start places, this is what I want to maintain. Rest of the things can be pumped down. So even in this kind of big structure, except for the leaves, if I see 2 non-terminals repeating, I can shrink that thing. So this part can be removed. And hence, because of this kind of shrinking, this skeleton, this red skeleton that I have on the tree, this is going to be of between 2 such nodes, it's going to be for the number of non-terminals. This stands for non-terminals. And the size of this leaves is going to be the length of x, or the length of the words that I've seen so far. So if I have a tree, binary tree with so many leaves, the size of the tree is also going to be that, multiplied by this number between any of the edges. The number of edges is also going to be linear. So it's going to be, the skeleton is going to be length of x times the number of non-terminals. And from any of these things, other trees can hang, and those trees I can brutally pump down. I have no problem because they are not used to covering. So those sizes will be atmosphere exponential. The height will be atmosphere length of non-terminals, so the size will be exponential. So these trees can also be pumped down, which will give us this upper bound for the context tree as well. With transducers, it goes one more exponential out because somehow you are taking the intersection with several runs. When you are taking an intersection of so many different things, that number is going into exponent. That's what's going to happen. So somehow you can in parallel have a context free grammar, or the past tree of the context free grammar and the runs of the transducer in parallel. That will give you one more exponential. As the upper bound. I'm wondering how I should go about it now. This is the double exponential hardness result, which basically just uses one crucial thing. Which is that if you have one push-down automaton and you have n finite state automaton, we can count up to double exponential using this.
So you want push down automaton and in
Finite state automaton, all of, let's say, linear, I mean, with some order of states, number of states and all that. Then we can count up to 2 power k. Using this. And when you can count something like that, you can also get the smallest words to be at least of that. So you cannot count down any. This is the idea that is going to be used inside. So I mean, so also one more interesting thing is there's this bounded version of PCP. Where the input is exactly like a PCP. In addition, you are also given a parameter L. And you want to know whether you have a solution whose size is actually going to be bounded exactly by this parameter. Okay, the length of the solution should be here. I put 2 power L. If I put 2 power L, then this particular problem is going to be double exponential hard. Actually, double exponential complex. Instead of 2 power L, if I put just L, it is going to be NG complete. If I just put 2 power L, it's going to be any expected complete. So canonical variant of the standard Turing machine problem in the PCP settings is we are bound on the solution here. So this is the place from where we will give a solution. I mean, give a reduction, but this is also very similar to the reduction that we had before. But the important thing is that I have to count to the 2 power, for which I will use this push-down and finite parameter for the transducers. If you want, I can go into this, or I can just completely skip it and go depending on it.
Yeah, we have 2 minutes. We have 2 minutes.
So-
So, I mean, we have 2 minutes, so
You want to see this? Or not?
Yeah, something like for the 2XP class, I mean.
Yeah.
Like, how would you show that the problem is complete? Such like, is there a canonical,
So it's basically.
Basically, with the bound.
sorry?
Basically, with the bound.
No, I'm saying, but like, how do you prove that that is complete?
Yeah, so it's actually,
Oh,
you take the standard reduction, show proof that BCP is undesirable
I see.
by
That's-
reduction from the
Sure.
then BCP and all that, the standard reduction that you have in the prof. You just plug in this thing, you will see that you take a standard Turing machine and you check for the exponential time bounded Turing machine, that will get translated into this one. That's what you.
I see.
So
So I thought you do, start things with the.
yeah, exactly, the booklet thing, the same thing will get translated into the L,
Yeah.
with the parameter in the PCB.
I see.
So,
Nice, okay. This would work for the whole.
yes.
Nice.
Yeah, so then I will just skip this. I'm saying this is not going into the steps also. This was the function automaton that was counting to exponential. And yeah, anyway, let me not go into that. Just I will tell you one more thing. This is some application of this whole thing. This is for acyclic lossy channel push-down systems. Lossy channel, which means of course you are communicating through channels and you can lose messages in between. So losing messages in between is essentially like subword order, right? And you kind of lose things in between. This get a scattered subword resulting in the channel. So this was known to be desirable if it was acyclic. Of course, if it is not acyclic, it's undesirable. It's known to be desirable, but the complexity upper bound was not known. So using this thing, we will show that this one is also a non-deterministic exponential time complete. So then there is a complete reduction through that thing as well.
All of these are in one paper? Or see that-
No, two papers. It's actually, I mean, I forgot to mention that. So it's a joint work with Prakash Saivasan from IMSC and with our PhD student, Soumodev,
Yeah, you
who's a
mentioned
student at
that.
CM.
At the beginning.
In the beginning, I mentioned that. So it's actually going to be his PhD thesis, this whole thing.
It was on your slide, I don't know if you said that.
Yeah, it was on my slides. I'm not sure that I mentioned it. So, yeah, just go here. Yes, so this is based on the paper set leaks and steps.
Okay.
The first question I was only do something like that, right? So if you do something basically, you would say, okay, supposing that there's a case size feedback gets can you remove, I mean, like, so basically,
No.
if you say.
So, okay, one would also ask, what if the like, what about bounded rivers, what about this?
Something like that, so instead of acyclic, let's say you have one cyclic relation between two variables. What, do you have some idea of what that?
Yeah, so actually, I do not know what exactly, so I do not know the precise boundaries in that sense that you're talking about. But at least the understandability result that I showed you from the PCP includes only 4 variables. There are only 4 nodes in the graph that I have. And so what edges I put, I have to go and investigate. But yeah, maybe if you
Yes,
remove
very
something,
small.
yeah, it's very small graph that I have, just 4. And the relevant language is also very simple.
Yeah.
4 variables.
Yeah, I only have 4 variables for the relation.
For the intersection. I mean,
That, yeah, the water spread thing, I only had 2 variables.
no, exactly,
Yeah.
yeah.
Only had 2 variables that was
Exactly, so there.
So water spray anyway is 1. So I'm talking about even with the regular and transducer or regular and shuffle, I had 4 variables.
Yeah.
For the PCP index, solution, F and G. These were the 4 variables I had.
So this is undecidability result.
Yeah, that's understandable. So what his question was, instead of asking for a cyclicity, can we go a bit more weaker, saying that we allow cycles, but only a weak form of cycle.
Yeah, just saying that even that is probably not.
I mean, yeah, so already we know that very simple graphs, like already 4 vertex graphs, it is 20 most of these graph theoretic bounds like variables.
So if you say 3 variables, then this kind of.
3 variables I do not know much. Actually, if you ask me, I do not know, we have not thought about it much, but maybe 3 variables it is, these design.
It is. Any other question? If not, then let's thank Aiswarya.
Okay.